Welcome to Lecture 3. This week we're going to finish Chapter 2. We're going to talk about one-sided limits, continuity, limits involving infinity, and asymptotes of graphs. First, let's talk about one-sided limits. Last week we started talking about limits. Last week we said we're interested in the behavior of some function if x is close to x. But let's suppose that instead of saying that, we want to say, how does a function behave if x is close to c and x is strictly greater than c? Or if x is close to c and x is on the right of c? Or, alternatively, how does a function behave if x is close to c but x is on the left of c, or x is less than c? This is the idea of one-sided limits. It's like a limit, but we're only looking on one side. First, some notation. X arrow c, this is what we were using last week for limits. This means x tends to c. If I write x arrow c and then superscript plus, or there's another way of writing the same thing. I could write x and then rightwards and downwards pointing arrow c. That means x tends to c from the right, or x decreases to c. If I write x arrow c superscript minus sign, or x and then upwards and rightwards arrow c, that means x tends to c from the left, or x increases to c. Now, of these two notations, personally, I prefer the second one, but your textbook uses the first one, which I've now put in red. So to be consistent with your textbook, I'm going to try to use this notation, which is in red. Limit, and then underneath limit, x arrow c plus of f of x is called the right-hand limit of f of x at c. And this means the limit of f of x as x tends to c, but if we only look at values of x on the right of c. And if I write limit and then underneath limit x arrow c minus f of x, this is called the left-hand limit of f of x at c. And this means the limit as x tends to c of f of x, but if we only look at values of x on the left of c. So for example, think about the function y is equal to x divided by the absolute value of x. If x is strictly greater than 1, then this function is equal to 1. If x is strictly greater than 0, the function is equal to 1. If x is strictly less than 0, the function is equal to minus 1. For the right-hand limit, we can forget all about the left part. We're only looking on the right of 0. How does the function behave? The function is always equal to 1. So the limit as x tends to 0 from the right of x divided by the absolute value of x is equal to 1. And then next, let's look at the left-hand limit. We're only looking at the left, so we can forget everything that's on the right of 0. How does the function behave if x is close to 0 but x is on the left of 0? The function is equal to minus 1. So the left-hand limit as x tends to 0 is equal to minus 1. Another example. F of x is equal to the square root of 4 minus x squared if x is between minus 2 and 2. And I'm looking at the end points at minus 2 and at 2. First, let's look at 2. Just here I have a left-hand limit. The limit as x tends to 2 from the left of square root of 4 minus x squared is 0. We can see that from the graph. The right-hand limit here does not exist. Now let's look at minus 2. The left-hand limit here does not exist because there's no function on the left of minus 2. the right-hand limit is equal to 0. Now, if we're in the middle, if we're somewhere between -2 and 2, then the limit as x tends to c, and the right-hand limit as x tends to c, and the left-hand limit as x tends to c all exist, and they're all going to be equal to the same value. Y is equal to x cubed minus x squared plus x minus 1. The limit as x tends to c exists for all c. The right-hand limit exists for all c, and the left-hand limit exists for all c. Now let's think about this function. Where does this have limits? Let's look at x equal to 0, first of all. I'm just going to be looking at 0, 1, 2, 3, 4, and 5. So 1, 2, 3, 4, 3, and 4. At 0, the left-hand limit does not exist. There's no function on the left of 0. The right-hand limit is equal to 1. The limit as x tends to 0 of f of x, all of the possible values of x in the domain which are close to 0, that's equal to 1. What about the x equal to 1? Look on the left of 1, the function is going down to 0. So the limit as x tends to 1 from the left of f of x is equal to 0. But the right-hand limit here is equal to 1, because on the right, the function is equal to 1. Because these are not the same, that means that the limit as x tends to 1 of f of x does not exist. At 2, the left-hand limit is equal to 1, the right-hand limit is equal to 1, and the limit as x tends to 2 is also equal to 1. And the same thing happens at x equal to 3. I'll go back to the previous example next. At 3, the left-hand limit is equal to 2, the right-hand limit is equal to 2, and the limit is equal to 2. And then finally, at 4, the left-hand limit we can see is equal to 1. The graph is sloping down and getting closer and closer to 1. The right-hand limit does not exist because there's no function after 4. And the limit as x tends to 4 of f of x exists because for all x close to 4 in the domain of the function, but apart from 4, the function is close to 1. Let's briefly go back to slide number 8. Pick any value of c, let's say here. And then if we can see from this picture that if x is close to c, the function is close to f of x. So the limit exists. We can say the same thing for the right-hand limit. If x is close to c, but on the right, then the function is close to f of c, and the same on the left. We're going to go into more detail later when we start using the precise definition, which I'm going to introduce now. Now, if you recall, the definition of a limit that we used last week said for all epsilon greater than 0, there existed some number delta greater than 0 such that if the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. We have almost the same thing here. For a right-hand limit, we want x to be close to c, but we're only interested in x on the right. So the way that we can write this, the way we can write x is close to c, but x is on the right of c, is by saying we want x to be between c and c plus delta. But apart from this, which I've written in red, everything else here is the same as for the limit definition that we talked about last week. And for left-hand limit, almost exactly the same thing. I want to look at x, which is close to c, but on the left of c. So we're going to insist that x is between c minus delta and c. Let me go back to the previous example now. Let's talk about this function again. And let's talk about at x equal to 1. Let's talk about the left-hand limit first of all. So we're forgetting everything on the right. Just forget that this function is just here. Only look on the left of 1. The function gets smaller and smaller. It gets closer and closer to 0 as x gets closer and closer to 1 from the left. So it looks like the limit as x tends to 1 from the left of f of x is equal to 0. Now let's look on the right. So we'll forget everything which is on the left. We're only going to look on the right of 1. So I'm going to cross out everything I'm not interested in. How does the function behave if x is close to 1 but on the right of 1? Well, the function here is always equal to 1. It goes 1, 1, 1, 1, 1, 1 as we get closer and closer to 1. I think it's clear from the graph that the limit as x tends to 1 from the right of f of x is equal to 1. I want to talk about the precise definitions of limits. Same idea as for the limit that we talked about last week, except that we're only looking on the left of x or we're only looking on the right of x. If we want, or if we insist that the function must be close to L, how close? Between L minus epsilon, L plus epsilon, and if we're only looking on the right, then we're insisting that x must be between c and c plus delta. For a left-hand limit, if we want the function to be between L minus epsilon, L plus epsilon, then we need to find the delta such that x is between c minus delta and c. Let's do an example. Prove that the right-hand limit at 0 of the square root of x is equal to 0. I've written the definition at the top for all epsilon greater than 0. So the first part of our answer is going to be let epsilon be greater than 0. Second part of the definition, there exists delta greater than 0. So the second part of our answer is going to be about delta. At the moment, I don't know what delta to write, so I'm leaving a blank here. And then the end of the definition is the conclusion. Intuitively, if x is close to c, but x is on the right of c, then f of x is close to L. Or more precisely, if x is between c and c plus delta, or for this example, 0 and 0 plus delta, then we want that the absolute value of f of x minus L is less than epsilon. For this example, we want the absolute value of square root of x minus 0 to be less than epsilon. So there's two things to do to finish this answer. We need to find the right delta, and then we need to fill in the calculation which proves that the absolute value of the square root of x minus 0 is less than epsilon. So let's get up the scrap paper and let's find the delta. What do we want? What do we want to end the calculation with? We want to finish with the absolute value of the square root of x minus 0 is less than epsilon. That's the same as saying the square root of x is between minus epsilon and epsilon, but square root of x is a positive number, so we can forget about the left part. We want to have that the square root of x is less than epsilon, so x must be less than epsilon squared. As soon as we know that the delta that we want is epsilon squared. Let's throw the scrap paper away and we can fill that in. And then we can finish the calculation. The absolute value of the square root of x minus 0 is the same as the square root of x because we have a positive number. If x is less than delta, then square root of x is less than square root of delta, but square root of delta is the same as epsilon. And that's the answer to this question. Theorem. If the left-hand limit and the right-hand limit both exist and are equal to the same number L, this is true if and only if the limit as x tends to c of f of x exists and is equal to the number L. I'm going to leave this for you to think about, for you to prove. The second part of the theorem, if the left-hand limit and the right-hand limit both exist but are not the same number, then the limit as x tends to c of f of x does not exist. My next section is about limits involving sine theta divided by theta. I've drawn the graph of this function. This function is defined everywhere except theta equal to 0. But what is the limit of this function as theta tends to 0? Theorem, the limit as theta tends to 0 of sine theta divided by theta is equal to 1, as we would hope it should be from looking at the graph. This is an important limit. We're going to need this limit again in lecture 5. So I want to prove it now. Look at the picture at the front. I have part of a circle of radius 1. I have some point P on this part of the circle. The point where the circle touches the x-axis, I'm calling the point A. Now, this height, the distance between P and the x-axis, must be sine theta, and this height must be tan theta. There's two more things I'm interested in. I'm interested in this green line and this red arc. Now I have three areas I'm interested in. I'm interested in the area of this green triangle, the triangle with corners at OA and P. I'm interested in the area of this red sector, the sector with corners at OA and P. And this area is bigger than the area of the green triangle. And I'm also interested in the area of this orange triangle. And this area is going to be bigger than the area of the red sector. So what are they? What's the area of the green triangle? This green triangle has base 1 and height sine theta, so the area of this triangle is a half sine theta. The area of this red sector must be a half theta because we're using radians, and the area of this orange triangle must be a half tan theta because its height is tan theta and its base is 1. So let's put these into the inequality down here. Green is smaller than red, is smaller than orange. A half sine theta is smaller than a half theta is smaller than a half tan theta. Multiply everything by 2. Sine theta is smaller than theta is smaller than tan theta. Divide through by sine theta, remembering that as long as theta is between 0 and pi over 2, sine theta is a positive number. So we get 1 is less than theta divided by sine theta is less than 1 over cos theta, because tan means sine divided by cos. Why is it tan? Let me go back. This distance is 1. This angle is theta. So therefore, by trigonometry, this must be tan. Okay, so where did I get to? I got to this point. Now I want to turn these fractions upside down. Yeah, I'm going to be using the sandwich theorem shortly. Instead of theta divided by sine theta, I want sine theta divided by theta. So I'm going to be doing this to the power minus 1. And when we do that, when each term is put to the power minus 1, we need to reverse the inequalities. Less than needs to become greater than. So that gives me 1 is greater than sine theta over theta is greater than cos theta. Because the limit as x tends to 0 from the right of cos theta is equal to 1, it follows from the sandwich theorem that the limit of the thing in the middle is also equal to 1. So that's the right-hand limit, but we also need to do the left-hand limit. But this is going to be easy because we're going to use symmetry. Sine theta is an odd function. Theta is an odd function. So when we do sine theta divided by theta, an odd function divided by an odd function must be an even function. So that means, and even if we didn't have the graph at the top, we now know, we have a function where the left part of the graph is just a mirror image of the right half. So if we know how the limit on the right behaves, by symmetry, the limit on the left must behave the same way. So just by symmetry, the left-hand limit as theta tends to 0 of sine theta divided by theta must also be equal to 1. Because the left-hand limit and the right-hand limit both exist and are the same, that means the limit as theta tends to 0, sine theta over theta is equal to 1. Remember this limit, we're going to need this limit later in the course. An example from your textbook, show that the limit as y tends to 0 of cos y minus 1 over y is equal to 0, and show that the limit as x tends to 0 of sine 2x over 5x is equal to 2 over 5. The first limit just relies on this identity. Cos y is the same as 1 minus 2 sine squared y over x. So what we have is there's a typo here. This should be the limit as y tends to 0. We have the limit as y tends to 0 of minus 2 sine squared y over 2 over y. At this point, I want to do a substitution. I want to replace every y over 2 by theta. So instead of sine y over 2, I have sine theta. Instead of 2 divided by y, I just have y. Now, if y tends to 0, how does theta behave? Theta also tends to 0. So we get minus the limit as theta tends to 0 of sine theta over theta. We know that limit, that's just equal to 1, multiplied by sine theta. We know the limit of sine theta, that's just 0. So it's minus 1 multiplied by 0, or 0. Now let's look at part B. We have sine 2x divided by 5x. We need to change this so that we can use the previous theorem. If we take a factor of 2 over 5 out, then we're left with sine 2x divided by 2x. That's just the same as the previous theorem, except we have 2x instead of theta. So the same theorem applies. This limit is equal to 1. So we end up with 2 over 5 multiplied by 1. Example 6 in your textbook, find the limit as t tends to 0, tan t sec 2t over 3t. Now remember, tan means sine divided by cos, and sec 2t means 1 divided by cos 2t. So really we have 1 over 3, 1 over t, sine t over cos t, 1 over cos 2t. Or 1/3 outside, sine t over t, we know how to handle that, the limit is just 1. 1 over cos t, we understand that, the limit is just 1. And 1 over cos 2t, again, the limit is just 1. So it's 1/3 multiplied by a function with limit 1, multiplied by a limit with function 1, multiplied by a limit with function 1, or just 1/3. Show that for non-zero constants a and b, the limit as theta tends to 0 of sine a theta divided by cos b theta is equal to a over b. And we want to use this sine theta divided by theta theorem. So what we're doing is we're multiplying and dividing by a theta and b theta, and then we're going to group them together. So we can write sine a theta over a theta. That looks like what we had before. B theta over sine b theta. It looks like 1 divided by what we had before. And then we have a number a divided by a number b. What is the limit of sine a theta over a theta? It's just the same as we had before. It's like sine u divided by u. So that's 1. What is the limit of something like v over sine v? 1 divided by 1, or just 1. So really we're just left with 1 multiplied by 1 multiplied by a over b. I think this limit shouldn't be there. So we're just left with a over b. That's enough about one-sided limits. Let's move on to the next chapter. I want to talk about continuity. Sometimes we can draw the graph of a function without lifting our pen off the paper. We put our pen on the paper, we start drawing, and we can draw the whole graph in one go. But sometimes we need to lift our pen sometimes. We can draw a part of a function, but then we need to lift our pen up, move our pen, and then put our pen back down on the paper and carry on drawing. If we have to lift our pen, then we get a function which is not continuous. That's the idea, but let's be more precise. A function f is continuous at a point C if and only if three rules are satisfied. We need f of c to exist. We need the limit as x tends to c of f of x to exist. And we need that these two numbers are the same. We also have something called continuous from the right. And the only change is that we're using right-hand limits here. And we have continuous from the left. And again, the only change is left-hand limits instead of ordinary limits. If f is not continuous at C, then we say that f is discontinuous at C. Or we say that C is a point of discontinuity of f. Let's look at this function again. Where is this function continuous? Where is this function discontinuous? First, I'm going to look at C equal to 0. Is f continuous at 0? And the answer is yes. Why? Because f of 0 exists and f of 0 is equal to 1. The limit as x tends to 0 of f of x exists and is equal to 1. And rule number 3, these two numbers are the same. 1 is equal to 1. So it's continuous at 1. Between 0 and 1, yes, it's continuous because the function is defined, the limit exists, and the limit is equal to the function. What about at 1? Is f continuous at 1? The answer is no. Why? Because the limit does not exist at 1. Between 1 and 2, at 2, between 2 and 4, and at 4. Between 1 and 2, yes, it's continuous, the function is defined, the limit exists, and the two numbers are equal. Is f continuous at 2? The answer is no. The function is defined at 2, f of 2 is equal to 2. The limit at 2 exists, the limit as x tends to 2 of f of x exists and is equal to 1. But these two numbers are not the same, so the third rule is not satisfied. Between 2 and 4, yeah, the limit exists, the function is defined, and the two numbers are the same. So yes, continuous, but at 4, the function is not continuous because the limit is not equal to the value of the function. F of x is equal to the square root of 4 minus x squared. This function is continuous at every c between minus 2 and 2. Intuitively, if we put our pen on the paper, we could draw this graph in one go without having to lift our pen in the middle. More precisely, the function is defined for every value between minus 2 and 2. The limit exists for at every c between minus 2 and 2, and the limit is always equal to the value of the function. This function. G has a point of discontinuity at c equal to 0, but G is continuous at every point which is not 0. Or this function. This function is continuous between minus infinity and 1. It's continuous between 1 and 2, and it's continuous between 2 and infinity. This function has points of discontinuity at c equal to 1 and c equal to 2. The floor function, or the greatest integer function, which I introduced before, this is the function which rounds down. It always rounds down to the next integer. So for example, the floor function of, let's say, 1.7, it goes down until we get to an integer. This is equal to 1. We can see from the graph, or we can see from the definition, that this function is discontinuous at every integer because the left-hand and right-hand limits are not equal there. It is, in fact, right continuous but not left continuous at every integer. If we're not at an integer, if we're between the integers, then the function is continuous. I'll move on quickly. I don't want to spend a lot of time on this example. If a function is continuous at every point in its domain, then we just say that it is a continuous function. Theorem. Suppose that f and g are continuous at a point C. Then f plus g is continuous at C. F minus g is continuous at C. Kf for some number k is continuous at C. Fg is continuous at C. F divided by g, as long as g of C is non-zero, is continuous at C. And f to the power n is also continuous at C. For an nth root, we need to be a little bit careful, and this is just me being extra careful here. We need the nth root of f to be defined on some small interval around C. If that's satisfied, then the nth root of f is also continuous at C. For example, every polynomial is continuous. If P and Q are polynomials, and if Q of C is not equal to 0, then the rational function P divided by Q is continuous at C. Sine and cosine are continuous at C. At every point, so they are just continuous functions. Composites of continuous functions. G composed with f, or G circle f, means first we calculate f of x, and then we calculate g of f of x. Theorem. Let's suppose f is continuous at C, and let's suppose that g is continuous at f of C. Then the composite function, g composed of f, is continuous at C. Now, you can think of it like this. If the blue arrow for f is continuous at its starting point, starting at C, and if g, also a blue arrow, is continuous at its starting point, f of C, then the red arrow, which goes all of the way from the starting point of f to the end point of g, is continuous at its starting point, continuous at C. Show that the square root of x squared minus 2x minus 5 is continuous on its natural domain. Natural domain means the biggest possible domain where the function is defined. Well, what can we say? We know that the square root of t is a continuous function. We know that x squared minus 2x minus 5 is continuous because all polynomials are continuous. So our function h is g composed with f. It's a continuous function composed with a continuous function, so it must be continuous. Show that x to the power 2 over 3 divided by 1 plus x to the power 4 is continuous. What do we have? X to the power 2 over 3, that's continuous. 1 plus x to the power 4, that's a polynomial. All polynomials are continuous. 1 plus x to the power 4 is always not equal to 0. So we've done everything that we need to check. It's a continuous function divided by a continuous function which is not 0. So we have a continuous function. I'm going to leave part C of example 8 in your textbook for you to read. There's another example there. Moving on, where is the function absolute value of x sine x over x squared plus 2 continuous? Well, we have x squared plus 2 on the bottom. That's a polynomial, that's continuous, and it's always greater than 0. We have sine x. Sine x is continuous everywhere. I have an x. X is continuous everywhere. And I also have an absolute value function, but absolute value function is continuous everywhere. So we've got continuous everywhere, continuous everywhere, continuous everywhere, continuous everywhere. Combine them together, we have a function which is continuous everywhere. One final idea before we take a break. I want to talk about limits of continuous functions. Let's suppose g is continuous at the point b, and let's suppose that the limit as x tends to c of f of x is equal to b. So in other words, g is continuous at the value of the limit of f. Then the theorem says the limit of g of f is the same as g of the limit of f. Now what that means is if we have continuous functions, we can swap the positions of the limit and the function. Limit of g is the same as the g of the limit. So for example, the limit as x tends to pi over 2 of cos of 2x plus sine 3 pi over 2 plus x. Cos is a continuous function. Because it's a continuous function, we can swap the limit and the cos. Instead of limit of cos, we can write cos of limit. Now, inside cos, I have limit of 2x. That's easy. That's just pi. Let's not talk about that. And then we have limit of sine of 3 pi over 2 plus x. Sine is a continuous function. Anytime we have limit of a continuous function, we can swap them around. Instead of limit of sine, we could have sine of the limit. And then after we've done that, this is an easy limit to finish. One more example. The limit as x tends to pi over 2 of tan 5x over 2 minus pi cos pi over 2 minus x. Now, tan, if you think about the graph of tan, it looks something like this. It does have some discontinuities, but it's continuous everywhere else. So as long as we're not at one of these discontinuities, then we can consider it to be a continuous function. I'm not going to do the details here. I'll leave that for you to think about. Think about why we're not at one of these discontinuities of tan. Assuming that we're not there, we can swap limit with tan. Instead of limit of tan, we can write tan of limit. And then the ideas are the same as the previous example. A simple limit. Limit as x tends to pi over 2 of 5x over 2. That's just 5 pi over 4. I have limit of cos. Cos is continuous everywhere, so that's the same as cos of limit. And then I'll leave the details of this for you to check later. And that's a good place for us to take a break. We're going to take a 7-minute break and we're going to continue at 3 o'clock. And now let's continue. I want to talk about a famous theorem called the intermediate value theorem. First, let's suppose that we have a continuous function defined on a closed interval. Let's suppose that y0 is any number between f of a and f of b. The theorem says then there exists some c between a and b such that f of c is equal to y0. Every number between f of a and f of b is the value of the function for some c between a and b. And we can use that for things like this. For example, show that there is a root of the equation x cubed minus x minus 1 equals 0 between 1 and 2. Well, we can calculate f of 1 is equal to minus 1, which is less than 0, and we can calculate that f of 2 is equal to 5, which is greater than 0. So let me just draw a quick picture. At 1, the function is equal to minus 1, and at 2, the function is equal to 5. And because this is a continuous function, that means we can draw the graph without lifting our pen off the paper. So if I start drawing at 1 minus 1 and finish drawing at 2, 5, my graph, however I draw it, must cross the x-axis somewhere between 1 and 2. In other words, by the intermediate value theorem, somewhere between 1 and 2, the function is equal to 0. It doesn't tell us the value of the root, but it just tells us that the root does exist between 1 and 2. Now, if we zoom in, look at A first of all. This is the number 1, this is number 2. We can see somewhere between 1 and 2, the function is equal to 0. Zoom in a little bit. This is 1, this is 1.5. And then we can see that somewhere between 1.3 and 1.4. Zoom in a little bit more and then a little bit more. We can see that it's somewhere here. Somewhere between 1.3240 and 1.3248. Another example. Use the intermediate value theorem to prove that the equation square root of 2x plus 5 is equal to 4 minus x squared has a solution. Well, we can see from the picture, it looks like it has a solution. It looks like there's a point where the orange graph intersects the blue graph, but I want to use the intermediate value theorem to prove this. Now, this is going to be the same as showing that this function f of x has a root. There's a solution of f of x equal to 0. What can we say about this function f? F is continuous between minus 5 over 2 and infinity. F of 0 is equal to minus 1.76, a negative number, and f of 2 is equal to 3, a positive number. So just as we had before, somewhere between 0 and 2, f must cross the x-axis. There must exist a root of f of x equal to 0 somewhere between 0 and 2. And that's what the intermediate value theorem tells us. By the intermediate value theorem, there exists some c between 0 and 2 such that f of c is equal to 0. Continuous extension to a point. Or we can think of this as filling in holes in a function. Consider the function sine x divided by x. This function is not defined when x is equal to 0. On the graph of this function, we have a hole at the point 0, 1. And then my question is, how can we fill in the hole at 0, 1? Let's be a little bit more precise. How can I define a new function, which I'm going to call capital F, which has two properties? I want capital F to be equal to small f on the domain of f, so that's everywhere except at x equals 0. And I also want capital F to be continuous. Looking at the graphs, I want capital F to look like this. I want it to look the same, except I want this hole to be filled in. Now, because the limit as x tends to 0 of f of x is equal to 1, we've done this, the limit of sine theta over theta is equal to 1. We're going to define capital F to be the function which is equal to sine x over x if x is not equal to 0, and we're going to define f of x to be equal to 1 if x is equal to 0. And then we've done what we wanted to do. If we're away from 0, capital F is equal to small f, but capital F is a continuous function because capital F is defined everywhere, and the limit as x tends to any number c is always equal to the value of capital F of c. We say that capital F is the continuous extension of small f to x equal to 0. So continuous extension just means writing down something like this. Capital F is equal to small f on the domain, and every time we have a hole, we're going to give a number to capital F so that capital F is continuous. Sometimes we can do that, sometimes we can't. Show that this function has a continuous extension to x equal to 0 and find that extension. Oh, there's a typo here. There's two mistakes on this slide. First of all, this should be defined if x is not equal to +2 and -2. And the second mistake here is show that this function has a continuous extension to x equal to 2. I will fix these slides after the lecture's finished. Now, note that f of 2 is not defined. However, we can factorize the top and the bottom, the denominator and the numerator, and cancel x minus 2 terms to get x plus 3 divided by x plus 2. So we're going to define capital F to be this function, x plus 3 over x plus 2. Then where small f is defined, small f is equal to capital F. But for capital F, we've filled in the hole. Capital F is continuous on its domain, so not at -2. And capital F is equal to small f for all x not equal to plus or minus 2. We can say that capital F is the continuous extension of small f to the point x equal to 2. Our final section for today's lesson is section 2.6. We're going to talk about limits involving infinity and asymptotes of graphs. First, finite limits as x tends to infinity or x tends to minus infinity. Look at the graph of y is equal to 1 over x. If x is strictly greater than 0 and x gets bigger and bigger and bigger, what happens to 1 over x? Well, it looks like 1 over x gets closer and closer and closer to 0. We want to write this as the limit as x tends to infinity of 1 over x is equal to 0. But this is mathematics, so we need to be more precise. We write the limit as x tends to infinity. F of x is equal to capital L if and only if for all epsilon greater than 0 there exists some number capital M such that if x is greater than capital M, then the absolute value of f of x minus L is less than epsilon. This is similar to the ideas from before. Still, we want to have that f of x is close to L. But how do we achieve this? Instead of saying x is close to a number, we want x to be very big. How big? As big as we need it to be. So bigger than some big number, capital M. For a limit of x tends to infinity, instead of using deltas, we use capital M to be some big number. We also have a similar definition for a limit as x tends to minus infinity. The only difference here is instead of x bigger than some big number m, we need there to be x smaller than some negative number of large size, capital N. Now, when we do limits, please think that anytime you see these letters, please think that epsilon is some very small number, delta is some very small number, capital M is a very large number, and capital N is a very large negative number. For example, prove that the limit as x tends to infinity of 1 over x is equal to 0, and the limit as x tends to minus infinity of 1 over x is also equal to 0. So our answer is going to look like this. As almost always, we start with the sentence, let epsilon be greater than 0. We're going to need to choose capital M, and we're going to need to choose capital N. And then we'll have our conclusions. X is greater than M implies something. X is less than capital N implies something. Let's bring up our scrap paper. Let's look at what happens if x is strictly greater than 0 first. We want 1 over x to be close to 0, or we want absolute value of 1 over x minus 0 to be less than epsilon. Because x is a positive number, that's the same as saying 1 over x is less than epsilon, or 1 over epsilon is less than x. So now we can see the number m that we want is going to be 1 over epsilon. And what about for the other limit? What about if x is less than 0? If x is a negative number, then 1 divided by x is a negative number. So when we remove the absolute value signs, we're going to have an extra minus sign here. And then I can rearrange that to minus 1 over epsilon is greater than x. Let me just note here that to go from minus 1 over x is less than epsilon to minus 1 over epsilon greater than x, we need to multiply both sides by x. But x is a negative number. When we multiply both sides of an inequality by a negative number, we change the sign. Less than changes to greater than if you multiply by a negative number. As soon as we've done that, we can see that capital N must be minus 1 over epsilon. So let's fill those in. We're going to choose M is 1 over epsilon, and we're going to choose N is minus 1 over epsilon. And then we can fill in our conclusions. If X is greater than 1 over epsilon, that's enough to prove that absolute value of 1 over x minus 0 is less than epsilon. And if x is less than minus 1 over epsilon, that's enough to prove that the absolute value of 1 over x minus 0 is less than epsilon. Prove that the limit as x tends to infinity of k is equal to k for any number k. I'm going to leave this one for you to do. Look back at how I proved it for limit x tends to c last lecture. You can adapt that proof, but for the new definition of limit as x tends to infinity. All of the limit laws, that's the sum rule, the difference rule, the constant multiple rule, etc., are also true for limits as x tends to infinity and limits as x tends to minus infinity. So for example, we can do things like this. The limit as x tends to infinity of 5 plus 1 over x is the same as the limit of 5 plus the limit of 1 over x. Or we can do this. This limit, I have the limit of pi, square root of 3, 1 over x multiplied by 1 over x. By the product rule, that's the limit of pi root 3 multiplied by the limit of 1 over x multiplied by the limit of 1 over x. Or pi root 3 multiplied by 0 multiplied by 0, which is 0. Okay, so for this one, you need to do the proof. You need to say let epsilon be greater than 0, and then choose capital M equal to something. And then you say, then if x is greater than capital M, this implies something. So just doing the same ideas as in the one before. Can we write the limit as x tends to infinity of k is equal to the limit as x tends to infinity of k? Yes, because you've written the same thing twice, as far as I can see. I don't understand your question. So you can use the sum rule if we're talking about this example, for example. The limit of 5 plus 1 over x is the limit of 5 plus the limit of 1 over x. Yeah, all the sum rule, the difference rule, the constant multiple rule, product rule, quotient rule, they're also true for the limit as x tends to infinity. So everything that we were doing for x tends to c, you can also do for x tends to infinity. Another example. Find the limit as x tends to infinity of this rational function. 5x squared plus 8x minus 3 divided by 3x squared plus 2. Now, the answer is not infinity divided by infinity because infinity divided by infinity is not a number. So what can we do for something like this? What we can do is we can look for the biggest power of x and then divide through by that. I have x to the power 2, x to the power 1, and then just a number. And then on the bottom, x to the power 2, and then a number. The biggest power in this rational function, the biggest power function is x squared. So what I want to do is I want to divide everything by x squared. 5x squared divided by x squared is 5. 8x divided by x squared is 8 over x. Minus 3 divided by x squared. On the bottom, 3x squared divided by x squared is just 3, and then 2 divided by x squared. And then I can use the product rule, the difference rule, and the quotient rule to see that this limit is 5 plus 0 minus 0 divided by 3 plus 0. So it must be 5 over 3. And this is a rule, this is a trick we're going to be using for any time you see something like this. Divide by the biggest power of x. I can show you the graph of this function. I said that the limit as x tends to infinity is 5 over 3. Hopefully the graph shows you that this is true. Let's do another one. Find the limit as x tends to minus infinity of 11x plus 2 divided by 2x cubed minus 1. Can you factorize it? You can try that. Sometimes it will work and sometimes it doesn't. But we were factorizing before when we didn't want to divide by 0. Now we have a slightly different problem. We don't want to have infinity divided by infinity. The specific rule that we try first is divide by the biggest power of x. I have 11x, I have plus 2, I have 2x cubed, and I have minus 1. What is the biggest power of x? The biggest power of x is x cubed. So I'm going to divide everything by x cubed. So I get 11 over x squared plus 2 over x cubed divided by 2 minus 1 over x cubed. The limit of 1 over x is 0. That means the limit of 1 over x squared is also 0. And the limit of 1 over x cubed is also 0. Then I have a number 2, and then another 1 over x cubed, which has limit 0. So 0 plus 0 divided by 2 minus 0. No problems having 0 divided by 2, that's just 0. Horizontal asymptotes. Sometimes a function y is equal to f of x gets closer and closer to a horizontal line as x tends to infinity or x tends to minus infinity. If this happens, then this horizontal line is called a horizontal asymptote of y is equal to f of x. And we find these just by calculating the limits as x tends to infinity or x tends to minus infinity. A line y equal to b is a horizontal asymptote of y is equal to f of x if one of these are true. Either x tends to infinity of f of x is b, or the limit as x tends to minus infinity of f of x is equal to b. Or both of them are true. For example, y is equal to 5 over 2 is a horizontal asymptote of 5x squared plus 8x minus 3 over 3x squared plus 2, as we saw earlier. For example, find the horizontal asymptotes of x cubed minus 2 divided by absolute value of x cubed plus 1. We need to calculate the limit as x tends to infinity and the limit as x tends to minus infinity. First, let's take the limit as x tends to infinity. And because we're going to be looking at very, very large positive numbers, it's okay for us to assume that x is positive. Why are we doing that? So that we can get rid of the absolute value. Instead of writing absolute value of x cubed, as long as we know that x is a positive number, we can just write x cubed here. And then we can do the same trick that we were doing before. The biggest power of x is x cubed, so divide everything by x cubed to get 1 minus 2 over x cubed divided by 1 plus 1 over x cubed. The limit of 1 is 1, the limit of 2 over x cubed is 0, and so on. We just get 1. Let's do the same thing for the limit as x tends to minus infinity. If x is a negative number, which is getting bigger and bigger and bigger in size, then it's okay for us to assume that x is a negative number. So instead of absolute value of x, we can write minus x. And then if we do the same type of calculation we did before, we end up with the answer minus 1. That tells us that the horizontal lines y equal to 1 and y equal to minus 1 are horizontal asymptotes of this function. And I can show you a graph of this function. The limit as x tends to infinity of this function is equal to 1. The graph gets closer and closer and closer to the line y equal to 1. The limit as x tends to minus infinity of this function is equal to minus 1. the graph gets closer and closer to -1 as x tends to minus infinity. Two more limits. Find the limit as x tends to infinity of sine 1 over x, and find the limit as x tends to infinity of x sine 1 over x. Okay, so on the graph, I'm trying to show that the graph is getting closer and closer to 1 and to -1. It never actually gets there. It gets closer and closer to -1. Okay, next question. Why we divide that by 2 over x cubed? So I'm thinking you're talking about this step. The limit as x tends to infinity of x cubed minus 2 divided by x cubed plus 1. If we had just replaced x by infinity, I would get infinity divided by infinity, but that's not a number. That's not the answer. The biggest terms here are the x cubed terms. So I want to divide through by x cubed. X cubed divided by x cubed is 1. Minus 2 divided by x cubed is minus 2 over x cubed. And then on the bottom, I get 1 plus 1 divided by x cubed. And all of these 4 terms can be handled easily. The limit of 1 is 1. The limit of 2 over x cubed is 0. The limit of 1 is 1, and the limit of 1 over x cubed is 0. Because we can handle all of these 4 ones separately easily, that means we can do the whole limit. I want to find the limit as x tends to infinity of sine 1 over x. And I want to do a substitution here. I want to replace the 1 over x by t. So I would have the limit as x tends to infinity of sine t. But note that when x tends to infinity, that's true if and only if 1 over x, or t, tends to 0 from the right. So I can also replace the x tends to infinity in the limit by t tends to 0 from the right. The limit that I want to calculate, limit as x tends to infinity, sine of 1 over x, is the same as the limit as t tends to 0 from the right of sine t. And that one we know how to calculate. We know that that is equal to 0. I've done a substitution. I've replaced 1 over x by t, and I've changed my possibly difficult limit into an easier one. Find the limit as x tends to infinity of x sine 1 over x. I'm going to do the same thing here. Again, I'm going to let t be 1 over x. Then the limit that I want to calculate is the same as the limit as t tends to 0 from the right. Instead of sine 1 over x, I have sine t. And instead of multiplied by x, then I have divided by t. This is one we did earlier. Limit as t tends to 0 from the right of sine t divided by t is just 1. Here is a graph of this last function. Y is equal to x sine 1 over x. We can see that as x tends to infinity, the graph is approaching the horizontal line y is equal to 1. Find the limit as x tends to 0 from the right of x multiplied by the floor function of 1 over x. And this is another one where we can do a substitution. We can replace 1 over x by t. So it's the same as the limit of 1 over t multiplied by the floor function of t. If x tends to 0 from the right, then 1 divided by x tends to infinity. So we just have the limit as t tends to infinity of 1 over t, floor function of t. I'm not going to talk about the rest of this example. You can read the rest. This needs to use the sandwich theorem to calculate the answer. For example, use the sandwich theorem to calculate the limit as x tends to infinity of 2 plus sine x divided by x. Well, we know that sine x is between -1 and 1. So it's sine x divided by x, and then take the absolute value of it. That must be between 0 and the absolute value of 1 over x. The limit as x tends to infinity of the absolute value of 1 over x. We don't need absolute value sign here if x is getting bigger and bigger and bigger. The limit of 1 over x is just 0. So it's another sandwich theorem question. We've got 0 on the left, 0 on the right. Function in the middle is squashed between 0 and 0. The limit of the thing in the middle must also be 0. So the answer to this question is 2 plus 0, or 2. And again, I can show you a graph of this function. As x tends to infinity, the graph is getting closer and closer and closer to the horizontal line y is equal to 2. Y is equal to 2 is a horizontal asymptote of this function. There's one more trick for limits. I mentioned this last week. I'll mention it again. Because a minus b multiplied by a plus b is a squared minus b squared, it follows that a minus b is equal to a squared minus b squared divided by a plus b. And this is going to be useful for us if a limit contains a square root sign. For example, calculate the limit as x tends to infinity of x minus the square root of x squared plus 16. We can't just replace x by infinity, because then we would get infinity minus infinity. And that's another one of these things which is not a number. We need to be more smart than this. So we're going to use the trig in this remark. I have something which looks like a minus b, so I'm going to multiply it and then divide by a plus b. I'm going to multiply by x plus square root of x squared plus 16 divided by x plus square root of x squared plus 16. So far nothing has changed, but this limit will now simplify. On top we're going to get x squared minus x squared plus 16. And of course then the x squareds cancel, we just end up with minus 16 on the top. And then at that point we can replace, so I can divide through by x, and then we can calculate these limits. Now, just one point, I'm doing x divided by x to get 1. But I'm also doing square root of x squared plus 16 divided by x. And when we take the x inside the square root, it becomes x squared. That's equal to the square root of x squared plus 16 divided by x squared. Because the limit of 1 over x is 0 and the limit of 1 over x squared is 0, we just get 0 divided by 1 plus the square root of 1 plus 0, or 0. I've talked about horizontal asymptotes. Next, we come to oblique asymptotes. Sometimes the graph of a function approaches a sloped line as x tends to infinity or x tends to minus infinity. This sloped line is called an oblique asymptote. And an oblique asymptote is a linear function. So the oblique asymptote is going to have equation y is equal to ax plus b for some number a and some number b. For example, find the oblique asymptote of y is equal to x squared minus 3 divided by 2x minus 4. I'm going to solve this 2 times. First, I'm going to use the method which makes more sense to me, and then in solution 2, I'm going to use the method which your textbook recommends. Have a look and see which one of these methods you prefer. I'm saying we need to find numbers a and b in this equation. I want to write that the rational function we have is equal to a linear function plus this green function, which is a remainder function. Note that the limit as x tends to plus or minus infinity of this green function is 0. So that means the function that we started with, x squared minus 3 over 2x minus 4, and this red linear function get closer and closer as x tends to infinity or minus infinity. So we're starting with this. We're starting with our function, x squared minus 3 over 2x minus 4 is ax plus b plus c over 2x minus 4, but we don't know a, b, or c yet. The first function I'm multiplying by 2x minus 4 divided by 2x minus 4 so that I can put everything over 2x minus 4. And then I'm going to compare the left-hand side of this calculation with the right-hand side. On the left, I have x squared, and on the right, I have 2ax squared. These must be the same. So 2a must be the same as 1. On the right, I have minus 4a plus 2bx, and on the left, I have 0x. They must be the same. Minus 4a plus 2b must be 0. And on the right, I have c minus 4b, and on the left, I have minus 3. Again, these must be the same. So we need to find a, b, and c such that 2a is 1, minus 4a plus 2b is 0, and c minus 4b is equal to minus 3. I'll leave it for you to check that we must have a is a half, b is equal to 1, and c is equal to 1. So that means that the function we want is y is equal to x over 2 plus 1. This is the oblique asymptote of our function. Let's do another one. Let's solve this problem using a different method. We need to divide x squared minus 3 by 2x minus 4 using long division. This is the method that your textbook recommends to you. And for those of you who have studied long division at high school, you might prefer this method. I'm dividing 2x minus 4 into x squared minus 3. What do I need to multiply 2x minus 4 by in order so that it looks like x squared minus something? I multiply it by a half x, and then I get minus a half x plus 4x. Subtract these, and we're left with 2x minus 3. And that looks similar to 2x minus 4. We have 1 multiplied by 1 to get the 2x term, and then there's 1 extra 1 here. So as I said, I prefer the first method, but some of you might prefer solution 2 if you've done this at high school or if you like the way that the textbook is explaining it. In general, we want to write our function y is equal to f of x as a linear function plus a remainder function. That's a function which has limit equal to 0 as x tends to plus or minus infinity. Then this linear function would be the oblique asymptote that we require. For example, this is on page 114, and it's exercise 108. Find the oblique asymptote of y is equal to x cubed plus 1 divided by x squared. This is actually an easy one because x cubed plus 1 over x squared is quite easy to see is the same as x plus 1 over x squared. The limit of the green function is equal to 0, so the oblique asymptote must be the red function, y is equal to x. Now, I'm aware oblique asymptotes is a tricky subject. We're going to come back to this in lecture 7. The final topic for today is going to be infinite limits and then vertical asymptotes. Again, look at the graph y is equal to 1 over x and think about the question, what happens to 1 over x as x tends to 0 from the right? The answer is 1 over x gets bigger and bigger and bigger and bigger as x tends to 0 from the right. We want to write this as the limit as x tends to 0 from the right of 1 over x is equal to infinity. Let's be more precise. I want to give two definitions, a different definition of the limit as x tends to c of f of x is equal to infinity, and the definition of the limit as x tends to c of f of x is equal to minus infinity. Now, if a limit is equal to infinity, that means the function is getting bigger and bigger and bigger and bigger. How big? Bigger than any number that we can think of. So that's the same as saying for all big numbers, capital B, we want the function to be bigger than b. For all big numbers, capital B, there exists delta greater than 0 such that if x is close to c, in other words, if the absolute value of x minus c is between 0 and delta, then f of x is bigger than b. And for going to minus infinity, again, we want some big number, capital B, but the change is that we want f of x to be smaller than minus b. There are similar definitions for the limits as x tends to c on the right and x tends to c on the left, but I'm not going to dwell on those. I'll leave those for you to write down. I want to move on to this one. Prove that the limit as x tends to 0 of 1 over x squared is equal to infinity. We start by saying let b be any big number. Let b be greater than 0. And then we need to choose delta. And normally I would bring up my scrap paper, but this time I've already done the calculation, so I already know that the delta that I want is 1 over the square root of b. Then, if the absolute value of x minus 0 is between 0 and delta, that implies that x is less than delta, and that implies that 1 over x squared is greater than 1 over delta squared, which is equal to b. And that's the proof. Let's talk about vertical asymptotes. Sometimes the graph of a function approaches a vertical line, x is equal to a, as x tends to a, or x tends to a from the right, or x tends to a from the left. This vertical line is called a vertical asymptote. A line x equal to a is a vertical asymptote of y is equal to f of x if either the limit as x tends to a from the right of f of x is plus infinity or minus infinity, or the limit as x tends to a from the left of f of x is plus infinity or minus infinity. So, for example, find the horizontal and vertical asymptotes of y is equal to x plus 3 divided by x plus 2. This function is defined if x is not equal to minus 2. So that means we're interested in 4 limits. The limit as x tends to infinity, the limit as x tends to minus infinity, the limit as x tends to minus 2 from the right, and the limit as x tends to minus 2 from the left. I'm going to leave it for you to check these 4. The limit as x tends to infinity of our function is 1. The limit as x tends to minus infinity of our function is also 1. The limit as x tends to minus 2 from the right is plus infinity. The limit as x tends to minus 2 from the left is minus infinity. That means the line y equal to 1 is a horizontal asymptote, and the line x is equal to minus 2 is a vertical asymptote. And I can show you a graph of this function. This is the graph of y is equal to x plus 3 divided by x plus 2. We can see that y equal to 1 is a horizontal asymptote, and we can see that x is equal to minus 2 is a vertical asymptote. Another example, find the horizontal and vertical asymptotes of y is equal to minus 8 over x squared minus 4. I'll leave it for you to check these limits. We're interested for the horizontal asymptotes, we're looking at the limits as x tends to infinity and the limit as x tends to minus infinity. For vertical asymptotes, we need to ask, when is the function not defined? It's not defined if x squared is equal to 4. So it's not defined at plus 2 and it's not defined at minus 2. Because these two limits are equal to 0, that means y equal to 0 is a horizontal asymptote. Because the limits on the right are either plus infinity or minus infinity, that means that the lines x equal to minus 2 and x equal to 2 are vertical asymptotes. Here is a graph of this function. And that's really all I want to say. There's one more example and one page of interest in your textbook, which I'm not going to cover. Please read example 17 and also read page 111 in your textbook, please. Next week, we're going to move on to chapter 3. We're going to start talking about derivatives. Are there any questions?